we are using new monitoring systems. So this is one, for example, voltage waveform sensor. And this is a sensor called phasor measurement unit. This is not very popular yet. Probably only a handful are actually installed in practice, including a couple of them in a feeder in Riverside for our projects. So what they do is that they measure the voltage phasor and the current phasor. This is the magnitude, this is the phase, for voltage and current, and 3 phases. And the key feature is that they are GPS synchronized, so that you can compare phasors at different locations. So that means we also have issues such as jamming GPS signals affecting the operation of the power grid. So putting all these together takes me back to the point that it's not just about those inverters. The whole grid edge is becoming very complicated, and for the most part, those lack of cybersecurity features exist almost everywhere in these systems. Okay. So then that takes me to this concept of physical botnets. The term botnet came from computer science, right? Some of you might have heard of this term. So the idea is simple. If you have a hacker that wants to cause some damage or make the server, push something out of service for a server, let's say a web server or email server, one way is that they directly try to attack the target, right? And hack into the system and shut it down. The other way is that they do what is called distributed denial of service attacks. That instead of trying to hack the target that is protected, they try to hack into some innocent computers across the network. They're called bots, like robots. And then those computers will try to attack the target. So many of them, they, for example, create traffic overload. And that traffic overload causes the damage. The server will be overloaded, so it goes out of service, right? So, with the idea that I was discussing based on grid edge, the same concept essentially can happen in power grids. When we're talking about trying to hack into a power plant, that's a one single hard attack. Many of those attacks are often just attempted attacks, or if occasionally they're successful, it's not just regular people trying that. It goes through more like cyber war, right? So the idea here is, just like the headlines that we had for PD inverters, the hacker can hack into several physical botnets, physical bots, which are essentially a network of such systems, which in this case are the grid edge, something that is not protected, was not supposed to have any cyber issue until very recently, right? And again, different studies have shown that the vulnerability is there. And then the impact is going to be essentially the same. Right? So that's the concept of physical botnet-based attacks against power systems. Now, when you discuss cybersecurity, there is a general term, what is the attack surface? So basically, what are the points of vulnerability and how we can work around them to have impact on the system? So when it comes to cyber physical systems like power grid, the smart power grid, control, sensing, and communications are the starting point of vulnerability. So there is a cyber component here that the attack can initiate from, whatever they want to do, including even jamming, phishing, or spoofing attacks, or even network traffic attacks. But whatever you do, it is essentially only on the cyber side, and it is meaningless unless there is a physical component linked to it. That means you essentially hack into those physical botnets, and they have a projection into the power vector in the power grid, and that's the notation that I told you, PL, for every bidder. And then what happens is that essentially you affect the power supply, power demand, or power flow, and only at that point there is an impact on the power grid. Right? Okay, so that's the background and motivation. So the idea is hopefully at least you feel some value in looking into this. Now, there are different types of attacks that you can think of. But the one that I picked is more related to my initial slide about you lose the power plant and then there's a disturbance in the power grid. So this attack is called destabilizing botnet attacks against power grid. And I'm going to talk about that. And then after that, we'll go through at least getting some examples of how this kind of attacks can be studied, given the fact that it's not just the cyber side, but it's also the physical side. Okay, so let's go back to that figure. I'm just showing one measurement for frequency rather than showing all of them, right? So this is the moment that you lose the power plant. So at that point, you have a sudden power imbalance, right, which creates a disturbance. Now, this part is one issue, you lost the power plant. This part is another issue, right? So what is this part? Remember, if you go back up, you're going to be back to normal. This is the response of the system. The overall system that you have, including like inertia, the physics of the system, and your sensing, control capabilities, everything together. So if the event ends up going like this, then pretty much this is a benign event. Right? You're back to normal. And by the way, in terms of timing, you see that it's a matter of, let's say, 1 minute, 2 minutes at most. You're going to be back to normal. Of course, if the first event is really severe, then you may lose stability even just at the very beginning. Now, if you try to hack into a power plant or whatever and try to create this sudden imbalance, essentially you create a disturbance to the system. Whether that disturbance is impactful, we will see. But there's a possibility to also try to affect the response of the system. That means you are not creating a disturbance, you are creating a stability issue for the system. And then it's going to be a computer code. You can make it in a way that is going to respond only if there's a major disturbance. So that means, if you have looked at frequency measurements, there's always some level of fluctuations in frequency. But once in a while, we have a major one. So you can set it up in a way that it comes up only at that point. But these two combined could both be cyber attacks, meaning that you can create the disturbance and also affect the stability, or you can just sit down and wait for a major disturbance and then kill the system. Right? And of course, I'm assuming that we agree that if the system cannot go back to normal, it goes to blackout, we have a major damage. Right? Okay. So with that idea in mind, the botnet attack strategy, going back to the concept of affecting the grid edge, can have two different strategies. One is, it could be a static attack. This is something that I initially studied 7 years ago, which is you have your power grid. This is the type of figure that you put for power. These are the generators, these arrows are the loads, those edges, and then there's a network. So essentially, you affect multiple points. You recruit your physical botnets. You affect them through internet connections. And these are your victims. This is a simple simulation. You create, let's say, this is a sudden increase in load, which is equivalent to sudden decrease in power consumption, in power generation, pretty much the same. Right? So there's going to be a disturbance. In this case, I'm looking at 3 frequencies. They are not F, they're omega because they're angular frequency. So the system can manage to get past by it. Right? But at the end of the day, you create a disturbance as if a generator was lost. Then more recently, I had a PhD student that started working on that second aspect, that you affect the stability or the response of the system through dynamic attacks that could be open loop or closed loop. Right? So essentially, they don't create a point of abruption. They create a trajectory that can affect the response of the system. Now, I'm going to talk about only the closed loop case. Like in this case, you have a sensor. That could be the attacker's sensor, putting a sensor on the grid. There's not a big deal. You can even plug in a sensor here. Or it could be the sensor of the system that you have hacked. Not a big deal. Then you have a control loop mechanism so that you don't just send a blind disturbance command to these buttons, but you rather control their behavior. Now, these feedback loops already exist for some of these grid edges because they're trying to actually be helpful to the grid, to stabilize the grid. So you just have to hack into the control algorithm, pretty much. And many of the systems already have some control mechanisms in place that essentially have this type of ultimate impact. Now, I have two examples here. Remember that BBC headlines based on a study in Europe was related to hacking into inverters. It's not just PV inverters. Battery inverters have the same impact. They have a very flexible control mechanism. You can actually implement a very cool advanced control algorithm, and you can implement that. Right? But I'm assuming that because they essentially follow a continuous control mechanism, we can just go for a proportional control. That's the very least. And many of them already have this type of control. Again, you just have to hack into that and somehow, let's say, change it from negative feedback to positive feedback. And then another system that is already in place, that is already responding to frequency, is over frequency and under frequency relays that many commercial loads already have, so that they essentially help with the stability of the system. Then the question is, what if they are hacked? You don't have in cybersecurity. Okay, so then a small simulation. What happens is that you start creating that trajectory. That trajectory, not high frequency. I will show you the frequency later based on some tests. And what happens is that you start deviating the frequency. There's a range. Let's just kind of exaggerate it for the purpose of simulation. And all you have to do is to push the very first protection system that would trigger to protect, for example, the power plant. And then when that guy is out, essentially you have started the cascading. Right? What happens after that, it's a story of its own. The system is changing, so you have to study the new system, right? Because you have lost the generator. But that's basically the target, essentially, in this type of attack. Just push the system up to that point. Okay. So that was just a basic introduction to the destabilizing attack. Now, attack detection, identification, and prevention. So the stuff that I'm going to explain is what I mean by physics and cybersecurity. Attack detection. Okay. So before you do attack detection, you need to do event detection. Basically, you have to figure out something is going on in the grid. And this is basically my major research focus, right? Now, there are different ways to deal with that. Right now, what I'm showing here is the measurements that we got from, at the feeder head at the substation for one phase for current, right? So you see that whenever you put a sensor, you're going to see a bunch of things like this, right? Now, there are different ways to deal with event detection. One is anomaly detection, especially for short-term events. So you have a window, for example, you can do absolute deviation around the median type detection. So what happens is essentially you define windows, and then you keep moving across those windows, and you define this bound, right, which is the deviation around the absolute median. And then if something goes outside that point, that means momentarily you have an anomaly, right? Now, I don't know if you can see it well, but there is an event here. right? Something is touching outside the upper limit. So that's an event that I'm not interested in. So let's move on. Now, you saw that that setup didn't detect these two major events. So one idea is that you slide the window, right, and do it again. Now, this time, again, I don't know how well you can see, but there's a teeny tiny overlap here. So that means there is an event. So let me take it out. Essentially, what I see here is the first event, and I put it here because I'm interested in this kind of events. Then you can cut the window in half and do this again. And this time, there is an overlap for this event, and I'm taking it out. So that's the second event of interest. If you look at these two events, they're fundamentally different, right? This is like there was a step function up, and then after, let's say, 300 milliseconds, there was a step down event, right? And this one has a dynamic. This one is second order or higher dynamic. Now, you can keep doing it if you want to basically identify all the events. So one way of starting point is to first extract these events, and then we can look at them. This is part of that anomaly detection procedure. So how do you process the events? I'm showing both events because they have different natures, so it's good to talk about both. So the first type of analysis is steady state. Essentially, the sensor that I had was a GPS synchronized phaser sensor. I'm only showing the magnitude, but you're also measuring the phase angle. Essentially, here you can say that we have a pre-event point and then a post-event point. Let's say this is the event. So that means you can model the pre-event phaser and then post-event phaser. And in one of our mainstream studies, we have been trying to look at these events to figure out where across the feeder this event happened, right? Which we use circuit theory type analysis, compensation theorem. That was the idea. So that's the steady state. There's a lot that you can do with the steady state analysis. Then the second one is transient type analysis. Essentially, you look at the exact signature, right? You have to define or extract the features of this image, per se, right? You can say that, okay, first of all, this is the